Hello, everyone. Welcome to today's Power Corner. I'm your host, Aalyia Shaukat, Editor-in-Chief of Power Electronics News. Today, we're sitting with Nikhil Jotwani, Systems Marketing and Business Development Manager for Automotive BMS at Texas Instruments. Thank you for joining me, Nikhil. How are you doing today?
Yeah, hi Aalyia. Thanks for having me here. I'm doing well. Hope you too, right?
Yeah, doing well, doing well.
Okay.
So we're here to talk about EVs, BMS. So EVs are evolving rapidly today. They're more electrified and intelligent, but all the progress isn't possible without the backbone of the EV battery and battery management system. So can you describe what does a modern BMS actually do, and how have semiconductor requirements changed as battery packs have grown larger, more complex, and more safety critical?
Yeah. So EVs or electric vehicles have evolved over the years, as you just said, and so have the functionalities, right, and the safety functions, including the batteries.
Mm,
The chemistries of the batteries have
yeah,
also developed. So if you see the NMCs, and then they moved to LFPs, and now we are looking at
yeah,
solid-state batteries as well, right?
yeah.
The modern day BMS is not only supposed to monitor the batteries and measure the parameters, but it's also supposed to ensure the safe delivery of power to the rest of the car.
Mm,
Similarly, when a critical fault occurs, the BMS is responsible for safely disconnecting the battery, right, from the load. We can address all such challenges with TI's broad portfolio. I mean, you're very well aware of
yeah,
TI's portfolio. We have about 80,000 products,
yeah.
right? And
A lot,
we
yeah.
so we have state-of-the-art analog front ends built
Yeah,
on ISO 26262 supporting ASIL-D
yeah,
functionality and coverage. Contactors and pyrofuses drivers also functional safe. Other functions like high voltage sensing, and not to forget the multi-core ASIL-D MCUs.
yeah.
So that's in all whole what the modern day BMS covers.
Yeah. Maybe we could dive into safety a bit more, right?
Hmm.
Thermal runaway is a high stake or the highest stake, one of the highest stake engineering problems in EVs. TI's BMS technology page, as you were saying, is a very, very broad portfolio. Um, using advanced detection and diagnostics, so can you describe different aspects of how TI uses edge computing? And there's one particular technology that was interesting, electrochemical impedance spectroscopy, or EIS for short, for thermal runaway detection of BMS. Can you describe those different aspects of that technology?
You got right into the core of the conversation. Okay.
Yeah.
So EIS is the talk of the town at the moment in the
Yeah.
EV world. Yeah. As we spoke, the batteries are evolving, and considering the challenges that we get in the batteries, understanding the state of the health, and you correctly mentioned thermal runaway.
Yeah.
I think let's just look at what thermal runaway means. It
Yeah.
is basically the exponential heating of a battery cell, which causes it to fail. And this may occur due to overcharging, internal shorts, or some damages that may
Yeah.
happen to a battery. The thermal runaway can have propagation risks, like it can go to the neighboring cell and so on. And if this happens, it can cause a complete system failure. To mitigate this, you would end up using sensors like pressure sensor, humidity sensor, temperature sensor, etc.,
Yeah.
which TI offers from its portfolio.
Yeah.
As you mentioned, electrochemical impedance spectroscopy, or EIS in
Yeah.
short, it is a key
It's a big word.
diagnostic. It is a
It's
big
a very
word.
long
Yeah,
one.
yeah, yeah. It was a tongue twister at the start, but I think now I got a
Yeah.
hold of it.
For me, for sure.
Yeah, it's a key diagnostic methodology, so
Yeah.
which provides us insight into the battery state of the health. It provides information like aging or lithium plating or degradation.
Mm,
And once we have all of this data, you can get an improved state of charge, and the accuracy of the state of charge, which is very
yeah.
important for electric vehicles.
Gotcha. And well, can we talk about that in a little more detail? It is innovative technology, and historically it's been relegated to labs because it needs precision test instrumentation, right? So from what I understand, EIS, you use it to characterize the internal electrochemical state of the battery by applying a small AC signal across multiple frequencies. So can you break down maybe EIS in more detail, but what can it, well, you described this, but what can it actually tell you that temperature monitoring cannot, in a little bit more detail?
Yeah. So EIS has, as you mentioned, has existed in the labs or in the industry for many years. There's been a lot of research that's been going on around it. And again, right, coming back to the point that the EVs are evolving and the battery packs are evolving, the complexity, the size, the amount of power that they can deliver. You need to use advanced technologies like EIS to overcome the challenges that they show, and not just rely on temperature measurement. EIS is basically, I think you touched on that, is the frequency response of the battery when you send a small AC signal applied over the different ranges, and what each frequency range, it reflects a different intrinsic parameter of the battery. I think one of the points that you asked about was the temperature measurement, right? What the temperature measurement cannot. In traditional BMS, temperature sensors have been used, but what they do is they are measuring the exterior temperature of the batteries. When you send a particular AC signal over a frequency and measure EIS, you are measuring the internal temperature of the battery. And that is the key difference between what a temperature sensor cannot do, right? So you are literally going to the core of the battery to understand the temperature at that point.
I understand. And it's, correct me if I'm wrong, but it's sort of more multidimensional, whereas like you would say you would need a temperature sensor, as you're saying, humidity sensor and pressure sensor to gauge more parameters. You could use EIS to instead understand all those aspects that you would need multiple sensors to gauge. Am I correct?
So yeah, so you use both the technologies in combinations. And just connecting it to thermal runaway from the previous question. In case of a thermal runaway, the event has already occurred and you need to detect it. EIS is more understanding the health of the battery and thus predicting what will be the longevity of the battery, and also understanding the other parameters, right? What is the temperature inside the cell? EIS is usually run at a given time based on the sequence that the tier one or an OEM would like to develop. But when a thermal runaway happens is not known.
Gotcha. Yeah.
So you would use it in combination.
Gotcha. Okay. And I'm continually harping on the EIS subject, but I have one more question there. What does it take to reliably implement EIS inside a production vehicle rather than the lab?
Yes. This is the challenge these days, right? A car is very tough and a very noisy environment. And what you need to do for EIS is, as you mentioned about the AC signal, you need to generate a reliable and a stable excitation signal. You need to read that signal out with high accuracy. In a car, as you can imagine, you don't always have the flexibility to place the PCB to your choice or lay out the cabling to the optimum way, right, due to the mechanical reasons. On implementing EIS in a car, here are some key care abouts that maybe we can talk of. Maybe, keeping the cables tight, using high-end, low-noise analog front ends with ADCs with high resolution. What also happens in a car is there's a lot of temperature swing that's happening, so you need to compensate for that, for temperatures. And as I mentioned earlier, EIS is, you can do an EIS sweep, as you mentioned, over the different frequencies. And you can do this in different stages of the drive, etc. And dependent on the dynamic load that you get, like accelerating or braking, etc.,
Yeah.
you may need to compensate for that as well. So it is definitely challenging at the moment to implement that. But if you do have some good resources, etc., it should be
Yeah. Feasible,
possible.
doable. Yeah.
Yes.
Okay. So we'll switch to contactors and pyrofuses.
Okay.
So when a thermal runaway event occurs, the BMS must disconnect the battery pack, and this is where the
Hmm.
contactor drivers and pyrofuse drivers sit.
Hmm.
Can you explain what these drivers actually do during a disconnect event, and how does the level of integration and diagnostics matter?
Yeah. So the disconnect unit, or we also call it the battery junction box.
Mhm.
At the start of our conversation, we were talking of the functionality of the BMS, of the modern day BMS,
Mhm.
where it is to transfer power safely to the rest of the car and also disconnect it in case of a critical failure. So mainly we are talking of the two components that you mentioned, the
Yeah.
contactors and the pyrofuse. So
Yeah.
let's go with the contactors at first, right?
Okay.
These are relay elements positioned on the high voltage bus. That is a 400 volts or an 800 volt, depending on the battery pack that you're using.
Mhm.
Um, when it is activated, or using a contactor driver, when you send an activation signal, it connects the battery pack to the load, and the load can be something like an inverter or high voltage compressor, etc. Similarly, when you're keying off, post running all the diagnostics, the contactor should discharge that relay and safely disconnect the battery pack from the load.
Mhm.
Um, to the pyrofuse, a pyrofuse is more like a last resort in your system to cause a
Okay.
permanent disconnect in your battery
Okay.
pack
Okay.
when a
Okay.
critical failure occurs. If you look at the way the pyrofuse is built up, it has a small piston, kind of an element, placed over a bus bar, which is then staying on your high
And it,
voltage or
yeah.
rail or on your low voltage rail. And when you send the activation signal, it would basically, the piston would push against the bus bar, thus permanently disconnecting the battery pack. Um,
Mm.
you can imagine a situation when a short circuit event occurs in your car, and there is a very high rush of current that is flowing to your load, right?
Mm.
And over here, this event is eventually recognized, or
Yeah.
by the current sense subsystem, which triggers an overcurrent event. And this trigger signal you would be sending to a pyrofuse driver,
Yeah.
which then sends the signal, causing the disconnect, as I just mentioned before. Um,
Mm.
as you can see, this subsystem is very critical, and you would need to have devices built on ISO 26262, have diagnostics to be integrated into them. So it's a very critical function of the BMS.
Okay. Thank you. Thank you for a little bit of background on that. Um, we could talk a little bit more bigger picture. TI offers a lot of design resources for BMS designers, including reference designs, app notes, and device ecosystems. For an
Hmm.
engineer designing a next-gen BMS, what do you typically see are the hardest challenges?
Okay. Um, TI offers definitely many design resources
Yeah.
to support the customers, to quickly prototype,
Mhm.
reducing the design cycles. Actually, that is one of the key focuses of my team. So I'm coming from a system engineering and marketing team,
Yeah.
where we are building many reference designs, focusing on one or the other key subsystems. We just spoke about the disconnect unit, right? So that is one of the subsystems, and we show how the various TI devices function together to overcome the challenges that we
Mm.
see. If you go to TI website, you would see many app notes, user interfaces, design guidelines, calculation sheets, etc., which are revolving around automotive BMS. And so automotive BMS being such a safety critical application, it's very critical to understand how to design it and also to extract the best performance out of the device, right? To which
Yeah.
you're using it. Let's take one of the examples, right?
Yeah.
Like cell monitoring unit, the one that's sitting right on the battery. The sensing lines, I think these are very critical on how you are designing them.
Yeah.
Because if you don't lay them out properly, the accuracy of the cell voltages that you're measuring may go off,
Yeah.
and this has a direct impact on the mileage that you see on your dashboard.
Yeah.
So in order to not have this, we offer EVMs, evaluation modules, guidelines directly from our experts. Also in BMS, some of the other challenges would be how do you measure high voltage reliably, or measurement of insulation monitoring, or designing the isolated power that is required in automotive BMS. So TI has the devices with its ecosystem, as
Yeah.
we spoke before, the app notes, the design guides, to
Yeah.
address each and every one of these challenges,
Yeah.
and resolve them. Our best resources, for companies, engineers, students, etc. I think you can just go to tia.com/HEV and you have the whole bunch of it.
Gotcha.
Yeah.
Um, thank you. Thank you, Nikhil. Um, just more future outlooks, right?
Okay.
Automotive electrification you were talking about, it's undergoing some pretty pivotal shifts, like
Mm-hmm.
including the shift to LFP
Mm-hmm.
chemistries, and that's gaining ground. And then there's solid state batteries on the horizon.
Mm-hmm.
How future-proof are today's BMS designs, and where do you see the biggest technology shifts happening?
Yeah. I think this is also connected to the previous questions that
Yeah.
we've been talking about. Batteries are evolving, the technology inside the cars are evolving, and this basically says that the semiconductors that support it are evolving along with it, right? When you visit our portfolio, you can see multiple generations of the devices that come alongside, be it on the AFE front or the MCU. While defining these devices, TI ensures that we are not only addressing the ongoing requirements, but also covering the future ones. And as I mentioned, it can be subsystems like on the diagnostic box or the low voltage domain where the MCU is based, etc. What's critical over here, where we work together, is with the tier ones and OEMs,
Yeah.
to ensure that the definition of these TI devices are also future proof, and then close the gaps to those requirements that we see to them.
Yeah.
And I think you asked about the challenge, not the challenge, the innovation, I guess.
Yeah.
Sorry, I forgot the second part of it.
The biggest technology shifts.
The
Where do you see the
technology,
biggest?
yeah.
Yeah, yeah.
Okay. Yeah. On that, what I'm really excited to see is how the automotive industry is going to adapt EIS, and which feature of the technology they will use and implement for their benefit, and try to differentiate from each other. As we spoke, right, EIS in the automotive world is very new, right? And
Mm.
we will see that tier ones and OEMs are going to spend more and more time and resources on it. So that, yeah, exciting times for us
Yeah.
on
That
BMS.
is that is very exciting. Well, thank you so much, Nikhil. I don't have any other questions. So no more questions here. I really appreciate your time. Thank you for answering all of them. Excited to see how TI's portfolio continues to expand for automotive BMS. Thank you.
Thanks a lot, Aalyia, for having, and thanks for the discussion today.